Let's move now to thread libraries. So these are libraries, I mentioned this before, that provide to the programmer an API, so some facility to manipulate and to manage, create, and destroy threads. There are two ways, of course. Libraries that allow you to define threads that should operate in user space, and others that can operate at the kernel level. Pthreads is probably the most known one, common one, in Unix systems at least. Okay, it provides both user level and kernel level threads. And what is important here is that we're talking about a specification, okay, not an implementation. Depending on the system you use and the version you use and the implementation you use of Pthreads, you will have certain possibilities enabled by the library, some specific details about how they behave and so on. Okay, so it's important to make this distinction, because you might ask, but if I call a specific function like the one I show you next, what will I get? And the answer to that is it depends on which implementation you use, because we are looking at a specification, not at the implementation. So let's have a look at a simple example. The example doesn't really make sense in terms of using a multi-threaded process, because as you hopefully will understand, you don't really need to create two threads to do this, but it's just from, let's say, an educational perspective. So we want to sum all the numbers between 0 and n is a number that is passed by the user, and we want to create a thread to do this instead of doing it with the original thread with which the process starts. We create some global variable, sum, and then we define here the function runner, and then we start with the main. So we create an ID for the thread that we are going to create, and we also create attributes for the thread. This is because at the time when we will use the Pthreads to tell the operating system we would like to create a new thread for this process, we are requested to pass some attribute, some information about how the thread should be created. We check the number of arguments. It needs to be 2, otherwise the program ends. And you know that the first one is the name of the program, so we actually have to pass one number. If we do, we check whether we can convert this number to an integer and that number is greater or equal to 0. Otherwise, we also return. Then this is what we do. So we use the library to simplify our interaction with the operating system. Okay. And what we do is that we create an initial setup for the attributes of the thread. Okay, we could manually specify them, but if we don't want, we can just set the default attributes. And then we call pthread create. So here we are telling to the operating system that through the library that we would like to create a new thread that belongs to this process, that we would like the ID of this new thread to be stored here in the ID of the thread, that these are the parameters, the attributes for the thread creation, that when this thread starts, it should run the function called runner that we defined before, and that we want to pass to this function what we have here, which is the number that is passed by the user. So if this function runs successfully, when it's finished, in our operating system, we will have this process with two threads. One thread will be the one that will run the next instruction here, so pthread join. The other thread belonging to the same process will have its program counter set to run runner. Okay, so it will start from this instruction. Now we have two threads. Let's assume that these are kernel threads, okay, for this example. Now, this can be scheduled by the operating system in different ways, okay? Each thread can run for a while, can go in waiting, can be put back to ready, there can be context switches because of interrupts, everything can happen, okay? We don't know in which order it's going to happen. So there is no guarantee that when the new thread starts, it will do everything and then exit before the original thread will run the next instruction, okay? So how do we synchronize these threads? Because our final goal is to print here the value of sum. Sum is a global variable, and since this is in the data section of the process that is shared by all the threads, if one thread modifies it, the other thread will also see that the value has changed. The problem is that before we print it, we need to be sure that the other thread, the new one that is running the runner function, has actually completed. How do we do this? Well, the library gives us another function, Pthread join, and we pass the ID here. And so what we are telling now the operating system is that we want this thread to stop its execution and go into waiting and wait until there is a signal by the operating system that tells to this thread that the other thread, the one that is running the function runner, has completed. Okay. Again, we don't know in which order threads will be executed. It might be that by the time this thread calls Pthread join, the other threads it's already done or not. But it doesn't really matter. The important thing is that for sure, by the time that this thread wants to run print, then the other thread will be finished for sure, because here we force the execution to stop until the other thread is finished. So what the other thread does is the following. It creates some local variable, it gets a parameter, it converts it to an integer. It sets 0 to sum. Sum is a global variable, it's not a local one. So this the modifications done on this variable will be visible also for the other thread. Then it runs the sum, and it uses again the library to tell to the operating system, I'm done, I'm finished, and everything went well. This is why it's passing value 0. As I said before, manual, read the specification of all these functions to understand well what they're doing and even more. Now, we can create one thread, or we can create a lot of threads. Okay, so we could create pthread create. We could call the function pthread create many times, and we would get, if we call it 10 times, we would get a process with 10 plus 1 threads, the original one plus the n1 we create. We can of course create an array like here, in which we keep the IDs of all the workers, and if we want to wait for all of them before going on with our execution, we can of course do something like this. So create a for loop and then wait for each one of them to complete. Again, it might be that by the time we ask the first one whether it has completed, it has already completed. By the time we ask the second one, that has not completed, and we have to actually wait. By the time we ask the third one, it has completed, and so on. We don't know in which order these things will be executed, but we know for sure that nothing will happen in the main thread until all of them have completed their execution.